everything changed yesterday. Now, what they've done is they have found this fundamental leap in computing chip that they have now made into a topological conductor by using an element, a molecule, that we didn't even know really existed up until a year ago.
For years, researchers have struggled with topological sorting, a fundamental process that organizes complex, interdependent systems. This challenge has hindered advancements in fields ranging from artificial intelligence to logistics and cryptography. But now, a groundbreaking approach powered by quantum mechanics has shattered the limits of classical computing, solving the problem in a way no one thought possible. Michio Kaku, one of the most well-known physicists of our time, has long predicted that quantum computers would one day surpass classical machines in ways that seem almost supernatural. That moment may have just arrived. Scientists at MIT and Google's Quantum AI Lab have tested a revolutionary quantum algorithm that isn't just incrementally better, it's exponentially faster. What would take traditional computers hours, if not days, can now be solved in mere moments. The implications are staggering. Artificial intelligence could evolve at an unprecedented rate, encryption as we know it could become obsolete overnight, and our very understanding of computation might need to be rewritten. But here's where things get even stranger. Some researchers fear that this level of computational power may be too much, too soon. Unlike classical computers, quantum machines don't simply process information, they explore multiple possibilities at once, working in ways even scientists struggle to fully comprehend. Could this breakthrough be the first step toward an intelligence beyond human control? Could it unlock a deeper understanding of reality itself? Before we explore the full impact of this discovery, we need to understand why topological sorting has been such a major challenge for traditional computers. What makes this problem so difficult? And why has it taken decades to finally crack it? The hidden challenge of topological sorting. At first glance, topological sorting may seem like a niche mathematical concept, but it plays a critical role in modern computing. It's the invisible force behind some of the most important technologies we rely on every day, from artificial intelligence to global logistics. At its core, topological sorting is about arranging tasks in a sequence where certain steps must be completed before others. Imagine planning a construction project. Laying the foundation must come before installing windows. In computing, this kind of dependency mapping is everywhere. 1. Artificial intelligence and machine learning. AI systems rely on topological sorting to process massive datasets efficiently. 1. It helps organize training data, optimize search results, and predict trends. 2. Logistics and supply chains. Airlines, shipping companies, and delivery networks use it to coordinate schedules, minimize delays, and improve efficiency. 3. Cryptography and security. Secure data transmission depends on intricate layers of encryption, and topological sorting structures encrypted communications and security protocols. Despite its importance, topological sorting has always been a challenge for classical computers. The problem: as the size and complexity of a dataset increase, the time required to compute the correct order grows exponentially. Even the fastest supercomputers process plotting algorithms step by step, evaluating one possibility at a time. This works for small tasks, but when dealing with massive, interconnected data structures, these systems quickly reach their limits, leading to slowdowns that bottleneck entire industries. This is where quantum computing changes everything. Instead of evaluating each possibility sequentially, quantum algorithms explore multiple paths simultaneously, accelerating the sorting process exponentially. This isn't just an improvement, it's an entirely new way of computing that could eliminate one of the biggest inefficiencies in modern technology. But if that sounds impressive, what happened when scientists at MIT and Google's Quantum Air Lab put this theory to the test was even more astonishing. Their discovery wasn't just faster, it was something no classical computer could ever hope to achieve. And it could change everything. The breakthrough that shattered expectations. The breakthrough came from an ambitious experiment led by researchers at MIT and Google's Quantum Air Lab. For years, scientists theorized that quantum mechanics could unlock new ways to process complex sorting problems, but no one had successfully demonstrated a quantum algorithm that could outperform classical methods, until now. Unlike classical computers, which process sorting step by step, a quantum computer operates fundamentally differently. Leveraging the principles of superposition and entanglement, quantum systems evaluate multiple possibilities at once. Instead of being restricted to a linear sequence of operations, the quantum algorithm explored an entire range of potential orderings simultaneously. The result? A massive reduction in sorting time. Tasks that took hours on the world's fastest supercomputers were now completed in mere seconds. To grasp the scale of this breakthrough, imagine a library filled with millions of randomly arranged books. A classical computer would have to examine each book one at a time to determine the proper sequence. A quantum computer, however, would consider every book's position simultaneously and instantly determine the most efficient way to organize them. That's the power of quantum computing. The implications are nothing short of revolutionary. 1. Artificial intelligence acceleration. AI models, which rely heavily on sorting massive amounts of data, could now learn at speeds never before imagined. 2. Cybersecurity and cryptography. Encryption systems built on complex sorting operations could be rendered obsolete, forcing an urgent shift to quantum-resistant cryptography. 3. Scientific simulations. Fields like climate modeling, drug discovery, and materials science could see dramatic improvements in accuracy and efficiency. But perhaps the most shocking realization: this breakthrough is just the beginning. If quantum computing has already surpassed classical methods in sorting, what other fundamental computing challenges will it unravel next? Michio Kaku's prediction becomes reality. For years, renowned physicist Michio Kaku has been one of the most vocal advocates for quantum computing. He predicted that these machines would eventually surpass classical computers in ways that seemed almost magical. Now, with this new breakthrough in topological sorting, Kaku's predictions are beginning to look less like speculation and more like an unavoidable reality. He has long argued that Moore's law, the principle that computing power doubles every 2 years, would eventually hit a wall. When that happened, he believed quantum computing would be the only way forward. Critics dismissed these ideas as overly optimistic, especially since quantum computers require extreme conditions like near absolute zero temperatures to function. But now, the results speak for themselves. Kaku has often compared quantum computing to the transition from vacuum tubes to transistors, a shift so radical that it redefined what computers could achieve. But quantum computing goes even further. While traditional computers operate using bits that represent either a 0 or a 1, quantum computers use qubits, which can exist in a state of 0, 1, or both simultaneously. This ability to process information in parallel universes of possibility exponentially increases their power. Even more stunning, Kaku specifically predicted that one of the first real-world applications of quantum computing would be in sorting and optimization, the very problem that MIT and Google's Quantum Air Lab just solved. He foresaw quantum breakthroughs transforming AI, cybersecurity, and scientific research, and now, that future is arriving faster than anyone expected. The future, a new era of computation. If quantum computers are already solving problems once thought impossible, what happens next? What are the larger implications for AI, cryptography, and the very nature of information itself. If Kaku was right about this, what else might he be right about? As researchers dig deeper into the power of quantum mechanics, many are beginning to realize that this is more than just a technological upgrade, it's a fundamental shift in how we understand intelligence, computation, and even reality itself. The consequences of this discovery stretch far beyond faster processing times. 1. AI evolution. Machine learning models could soon train in days or even hours, allowing AI to surpass human cognitive abilities far sooner than expected. 2. Cybersecurity disruption. Quantum computing's ability to break classical encryption could force governments and corporations into an urgent race for quantum-safe cryptography. 3. Scientific breakthroughs. From modeling the human brain to simulating quantum mechanics itself, the possibilities are limitless. This isn't just the future of computing, it may be the future of intelligence itself. And as quantum breakthroughs continue to unfold, one thing is becoming clear: we are standing on the precipice of a new era, one that could redefine everything we thought we knew about technology, computation, and reality.